Hello, good morning, good afternoon, good evening, wherever you are. I'm very excited to be joined along with Chris Casson and Mike Anand. My name is Arun Gupta. I'm a principal open source technologist at Amazon Web Services. Very happy to be talking about how do we do distributed tracing for Kubernetes applications or modern applications on AWS. Let's get started here. Now, before we look into how do we do distributed tracing for distributed applications, let's talk about what does a modern application look like. These modern applications typically leverage containers and serverless because there is a lot of similarity between the two architectures. What containers enable you to do, what serverless enables you to do, they really make you think about building those stateless applications, and they really allow you to, they encourage you to build microservices-based applications, apply that architecture, and be fully distributed. The primary benefits of such modern applications are that each component or microservice is independent, which leads to continuous improvement, delivery, and deployment of the application. Such an architecture also helps you in fault isolation, wherein errors and faults are really isolated to a particular microservice. These benefits in general leads to a robust application that enables constant development and improvement from a developer perspective. Kubernetes has a broad spectrum of benefits in general. If we're looking to build an application with Kubernetes, now starting from its support for the open source community, all the way to being portable across multiple cloud environments. It is really geared towards building modern applications that leverages containers and microservices platform that we covered before. Kubernetes actually provides certain basic primitives that really encourages microservices-driven application development. You can look at things like service, deployment, replication controller, the inbuilt service discovery. Those are some basic primitives that Kubernetes provides to help you with the modern application development. Now, if you have noticed, Kubernetes has had the tipping point in the last few months where it has gotten a lot of developer traction. But when we talk to our customers, they tell us that running a Kubernetes cluster is hard. So one of the top requests that we were getting from our customers is, help us build a Kubernetes cluster. Help us run and manage and operate a Kubernetes cluster. As a result, our 90 to 95% of our roadmap is driven by customer feedback. So we announced Amazon EKS at last year's reInvent. Let's take a look at it, what Amazon EKS is. Amazon EKS is a managed Kubernetes control plane. Now, if you think about from the Kubernetes perspective, there is a control plane that consists of API server, controller, scheduler, and other components, which are stateless components. It also has etcd, which is where the state of the Kubernetes cluster is stored. So it gives you a highly available master and etcd. What that means is, from a customer point of view, you go to AWS console, use AWS CLI, and ask the console to create a Kubernetes cluster, and you get a highly available master or a control plane. Very much like ECS, which is AWS managed container service as well, you bring your own worker nodes. Those worker nodes can then be attached to the control plane, and that constitutes your data plane, essentially where your containers are running. So essentially, a quick summary, Amazon EKS gives you a highly available control plane, and then you bring your data plane and attach it to the control plane, which constitutes your entire server. Now, as we were building the Amazon EKS service, there are certain core tenets that we align with all the time. So, for example, here are the 4 tenets that we have been service is fully aligned with. First of all, some of the biggest enterprises in the world and largest enterprises in the world are Amazon customers. And they would like to run production grade workloads. They expect availability, reliability, security, high availability from this service. So one of the core tenets of Amazon EKS is, this is a platform where you can bring your production grade workloads and run it without a hitch. One of the core requirements from the customers have been that please do not fork Kubernetes. Please give us that upstream experience. So Amazon EKS provides a native and upstream experience. It is also CNCF certified. What that means is, at this point, Amazon EKS is version 1.10. CNCF, which is the foundation where Kubernetes project is sitting, has a certification. And all it means is that when you are launching a Kubernetes managed service, you can pass those certifications to be compliant with that particular version. Amazon EKS is 110 certified. So what that means from a customer point of view is that if you are running your applications on Kubernetes 110 in your data center, in your laptop, or anywhere else, you can bring the exact same application, and that would work on Amazon EKS as well. Another core tenet of EKS is where we provide a seamless integration with rest of the AWS services. So if you want integration with AWS CloudWatch, AWS CloudTrail, Code Pipeline, or Xray, we will talk about that later today, we will offer those seamless integration. You are certainly not forced to use any of those additional services, but the fact that we have a seamless integration makes it very easy and clean for you to take a look at it. And last but not the least, this is the part that I'm most excited about because EKS team will actively contribute to upstream. We have an open source team as part of Amazon EKS. There is, of course, a service delivery team, and there's an open source team. And as part of the open source team, their main charter is to contribute upstream. And this also goes back to our second core tenet here, where we're going to provide a native and upstream experience. Anything and everything that is going to be part of Amazon EKS is going to be coming from upstream. As a matter of fact, we recently hired Gyuho, who is the core maintainer of etcd, and we are constantly looking for people to join the EKS team. So talk a little bit about the architecture of EKS itself. Now, when you are creating a Kubernetes cluster, as we said earlier, you have a data plane, which is at the bottom layer, which is where the controllers, which is where the containers are going to run. And then, of course, you have a data control plane, which is sitting on the top. In the control plane, you of course have controller and etcd. Now, when you ask us to create a EKS cluster, the layer at the top, which is a control plane, so controller and etcd is provisioned for you. And behind the scenes, like let's say you pick a region, in that region, we will create 3 controllers for you and 3 etcds for you, and they're automatically highly available. So from your perspective, you get a FQDN, and that is a fully qualified domain name for your API server. And then at the bottom layer, those are the data plane, and those are the worker nodes running in your account. So the control plane runs in AWS managed account, and the data plane runs in the customer account. So a little bit simplistic view of this is, you get a FQDN for your cluster, which is your API server essentially, and you have your worker nodes that are connected to the control plane. And once they're connected, you can use the upstream kubectl or kubectl, however you want to call it, to talk to the API server and do the things that are necessary to be done. Now, some of the customers who are adopting EKS are shown on this list. I would encourage you to read one of the stories by GoDaddy on why they are adopting EKS. Just search for GoDaddy EKS adoption article, and you will find a lot of good details over there. So let's switch back to what are the challenges of monitoring distributed applications. Let's quickly look into what are the current challenges with monitoring your modern applications built on these solutions. Your traditional way of adding log statements and breakpoints do not work well at this scale. Since you have multiple microservices with different code bases, potentially different languages, it'll be very extremely hard to test them with log statements. Also, testing them locally in your workstation does not work in scale, since errors from different microservices cannot be tested locally because they potentially could be sitting across multiple hosts. Another point to understand here is the existing black box solution also does not work. Black box monitoring solutions provide high-level details that do not provide enough insights into your specific operations. With the massive scale, potentially running lots of microservices across lots of different containers, you need to look into specific issues with any or collective operations and gather actionable insights. So if you want to look at from a user-centric approach, let's say a user makes a request, it goes to Amazon API gateway. which then invokes a serverless function in AWS Lambda, which then talks to an Amazon SQS queue, which then potentially stores some data into Amazon DynamoDB as well, and the user gets a response back. If you are looking at it from a user perspective, you should essentially be getting a one trace end-to-end, independent of how many services their application is being deployed to. That approach is the best for the customer perspective from the user perspective, and that is the key approach that we're going to take here. So why does tracing individual requests matter? Well, you need to discover multiple services that make up your application. Discovering your multitude of microservices is the first step to identify any further issues. You want actionable insights to your requests and operations. These are important to provide you with detailed information that you can use to get specific insights. As your modern applications are naturally good at fault isolation, you also need to know when there is an issue with a disparate microservice. And last but not the least, once you discovered your different microservices, found specific request level information, you will now need specific root cause to pinpoint specific issues. Tracing provides that level of granular and deep dive information. So what is the solution that we're going to use today to help you monitor and generate distributed tracing across your application? AWS Xray. AWS Xray helps developers analyze and debug applications built using microservices architecture, and most importantly, quantify the customer impact. And we will see in the demo on how this is going to be available to you. At a very high level, how does the Xray service works? Well, first of all, once you have Xray enabled for your different services, you can easily generate trace requests. Those trace requests are then sent to the Xray service. They are stored as part of the Xray service. From those different traces, you can generate a holistic service map, which basically shows how different microservices are invoking each other. And then you can start clicking on a service map, click on a particular service, and you can start identifying what the issues are. And you will see a live demo of that in the talk later today. AWS Xray supports multiple languages. It's very much integrated as part of the standard AWS SDK. So whether you are using Java, Node, Python, .NET with .NET Core 2, Go, which is in beta, and Ruby, which is in beta support, is available. One of the cool things is how you can easily add filter to automatically capture metadata. You can just say, show me the responses only going to the database, or show me the traces only for Amazon SQS. You can also include traces for non-AWS services over HTTP and HTTPS. You really have to easily instrument your application, and then you start generating that trace information for your applications. A little bit more details about the Xray API. Once you have instrumented your code, it allows you to send, filter, and retrieve the tracing data. The tracing data by itself can be sent directly to the service without having to use the SDKs. What that means is you can actually write your own SDKs and support the languages that are not currently supported. You can also get raw trace data using batch get APIs. And once you have the raw trace data, you can generate your own analytics on top of that. So that's sort of the value add that it provides, that not only you can use the analytics provided by the Xray service itself, but you can create your custom analytics as well. AWS Xray provides you all the capabilities of traditional tracing solutions plus some more. Let's take a look at that. You can quickly analyze and debug issues with your EKS containers, as we'll see in the talk. Once you have instrumented your code, you can quickly get an end-to-end view of individual microservices. This one is very important, specifically pinpoint any issues. If your microservices are distributed across multiple containers, across multiple hosts, just simple logging statement will not be enough. From AWS perspective, we strongly believe in the open source community. So all of Xray SDKs are open source. We currently support 6 languages, which we talked about a little bit earlier. Xray is portable across any cloud services and does not limit you to AWS services. So you can use Xray on cloud services, on-prem services, and hybrid services as well. Now, what are the benefits of using Xray with EKS? Well, you can quickly discover microservices in your call graph Xray provides you a service map to visualize the end-to-end systems. And you will see a live demo of that today. To ensure efficient tracing and to provide a representative sample of requests, you can use the sampling feature in Xray. It will also help you control your costs. Using Xray, you can pinpoint specific issues to your specific container. This one is important to look at granular container level issues. And again, we'll see a live example of that today. While using your microservices architecture application, Xray can help you quickly identify a downstream issue that might be causing issues to other services. And this is very critical because you don't know what all downstream services are being called. Now let's quickly look at a couple of use cases for Xray with EKS. There are many more use cases that you can solve with Xray and EKS over and above these two. We will quickly troubleshoot our application to identify issues using Xray in the demo today. Then we'll go from there to identify who are your end users and who were impacted by this issue. With that, I'll pass on the mic to Chris.
So let's take a look at the demo application we have built. So we have a simple web application, and that has two downstream services. So we have 3 microservices, and then we also have built a Lambda integration sitting behind an API gateway that stores information into DynamoDB. Web app, greeting, and name, they are containerized. Web app is hosted in an EKS cluster. It receives traffic from the internet using a load balancer, and then sends a request to greeting and also sends a request to name. And obviously, greeting will return a greeting and name will return a random name. It uses that information to combine it and sends that back to the user, and also stores that using the Lambda function into DynamoDB. So you can think of the Lambda part as a sort of tracking or analytics application. But we'll get back to that later. Let's focus on the containerized part first. So we have this simple setup running in our EKS cluster, and now we'd like to understand how requests flow through this system. So let's take a look at what we deployed. So first, we're going to take a look at the EKS cluster. So this is the Amazon EKS cluster view. You see that I have pre-created a single cluster. I named my EKS. If I go in there, I can see the endpoint, I can see the version, I can see the certificate. So I have all I need to set up this cluster in kubectl. So, and this cluster was simply created using ekscdl.io, so which is a very simple way to create clusters from the command line. And then we have deployed our application, and I hope you can see this to the cluster. So I can show you the nodes quickly. It's just a simple 2-node cluster, so I only have 2 nodes in here. And we have deployed our application using Helm. Now, if you don't know Helm, it's a package manager for cloud-native applications. So we use that to bundle up all the 3 apps and deploy them automatically. And I can show you that this is the case. So I'll show you the 3 pods that are running. So we have the web app pod running, we have the name pod, and we have the greeting pod. We're simply running a single copy of this. So let's take a look if this is actually working. This is the load balancer endpoint that we requested. So I'm going to hit reload a couple of times, and I see a greeting. Oh, there's an error. Let's reload. Still an error. Let's do a couple more reloads. So we see hello Bernadette, hello Leonard. You guess where these names are coming from, but there's a couple errors in there. So now we need to understand and where the errors are coming from, and obviously we want to fix these errors. Now, we could say, okay, let's take a look at CloudWatch. So I'm going to go in CloudWatch. I'm going to take a look at CloudWatch logs, but there's nothing in there. So nobody has set up CloudWatch logs, so we don't see anything. So what can we do? Yeah, well, we can take a look at the pods. And now we're just running a single pod for every application. So this is going to be easy to spot the error. I have an alias on kubectl, so I'm just running k logs name, and I'm just going to print the last 100 things. And there we see an error. Now, in reality, you don't have a single pod for most of the services. So it's always going to be tricky to figure out, okay, where is this error coming from? Which pod is generating this error? So this won't really help taking a look at the individual pods. And this is where Xray can really help. So let's take a look at what we need to do to get Xray working for our applications and get it integrated into our applications. So I'm going to switch over to the code. I can quickly show you the Helm chart first. So you see how we deployed the application. This is the Kubernetes deployment for the web app. And you see there's a couple of variables in there, and these will be filled out when Helm deploys this package. And here you see where the images are coming from. They're coming from my Docker Hub. I also have an environment variable set for AWS Xray, and I also have the Lambda tracker set up. So let's take a look at the web application. Now this is the Java application. So we're using the Java SDK for AWS Xray. Xray also supports other programming languages such as Go, Python, Ruby, Node, and .NET. So the way you integrate this will be a bit different, but almost similar to what we have here. Something Java specific is the servlet filter. So we're integrating the Xray servlet filter into our web XML. And that way, all the incoming requests to our application will be traced automatically. So if a request comes in and it doesn't have a tracing ID attached, the filter will attach it. If it doesn't have a tracing ID, the filter will pick this up and then use that trace. And we're just doing that for all and every request, and we don't care. So we see everything. So that's the first thing you need to do to instrument your application to use Xray for distributed tracing. Next thing we need to do is we need to add Xray to our startup code. So when our app comes up, we initialize the Xray recorder, and we can set up a couple of parameters here. We're only doing a couple of things here, and the most important one is we're setting up 2 plugins. These plugins will give us additional information. So we're using the EC2 plugin, which is kind of obvious because we're running on AWS EC2 instances. And then we're using the ECS plugin. Now it's named ECS, but it also works for Kubernetes clusters. So if you deploy this on a Kubernetes cluster, and it doesn't matter if it's an EKS cluster or if it's a kops-based cluster or a different setup, use the ECS plugin because that will give you information about the container this is running in. And that's about it we need to do here. So next thing we're going to take a look at is the actual controller. I'm going to open the imports so you can see what I'm importing. I'm importing something for Xray here. I'm importing something that will instrument the HTTP client I'm using. And then when we go down, we see, okay, generating a random number, setting up a couple things in terms of timeouts. So we see if an application is slow, then it will time out and generate an error. And then I'm adding Xray tracing capabilities to my HTTP client. And that way, I don't need to instrument anything because the Xray SDK will take care of that for me. So we'll take the tracing ID, attach that to the outgoing request, and that way Xray can pick that up and send it back to the Xray service. So I'm sending out the request to the greeting service here, which is the first downstream service we're hitting. Then I'm sending it to the name message service, and then I receive that information, I put it together, I send it to the Lambda tracker, and then I also return it to the client. So that's all we need to do to instrument our application and get it ready for Xray. And for the other ones, for name and greeting, we did the same. There are also Java applications, so the setup is similar, and we're going to give you the repository so you can take a look at the code for yourself. So that was the first thing that we needed to do. Now the next thing we need to do is we need to add something to our Kubernetes cluster that will pick up this tracing information and send it back to the Xray backend, so to say. So we're going to deploy the Xray daemon, which is a daemon component. You can containerize and host it within your EKS cluster, and that will pick up these traces and send it to the Xray service. So I'm going to quickly show you how to do that. So we have Dockerized the Xray daemon. The daemon itself is open source on GitHub as well. And there's a download URL, and we simply grab that latest version, we unzip it, we set up the container, and then we have an entry point, and we make sure it listens on all ports. So we have that Dockerized, and then we're deploying the Xray daemon as a so-called daemon set onto our Kubernetes cluster. Now, the daemon set is a special type of deployment where Kubernetes makes sure that this pod is running on every node inside your cluster exactly once. And if you add a node to the cluster, it will also automatically deploy all the daemon sets to that node. So this way, we can be sure that no matter where our pod is running, we can always talk to an Xray daemon on the same node. So we save a bit of network traffic, and we don't need to worry about finding these Xray daemons because we know they're always on the node as well. So this is a standard daemon set deployment. We're pulling the Docker image from Arun's account here. We configure this using a config map, and this is just the standard Xray daemon config file that we inject as a config map into our deployment. I'll just take a look at this after the webinar. So we have the Xray daemon, we can deploy it, and of course I already did that, so I can show you. So there's the Xray daemon deployed. We have 2 nodes in our cluster, so we have 2 copies of the Xray daemon, 1 per each node running. Now, there's one final thing that we need to do. We need to make sure that this Xray daemon is allowed to write back to the Xray service. So we need a bit of IAM setup. I'm just going to quickly show you. I need to go to Chrome. Good. It locked me out. Now this is not good. This is the wrong one. Yeah, sorry about that. I'll quickly go on to log in so I can show you the IAM setup. Because we need to make sure that we have the right permissions attached to that. So I'm going to go into rows because the node group that was created using EKS CDL, this one here, and we need to attach the Xray write-only access policy to that role. So that way, everything on the node can write to the Xray service. Now, this is something you don't want to do in production. It's fine for dev and test. For production workloads, you want to limit this down further, and ideally, you want to attach this only to the Xray pods running. So use something like IAM to enable that in your Kubernetes cluster. Now, we have everything in place. We have our EKS cluster up and running. We have deployed our application. We have deployed Xray, and we set up the permissions correctly. So we can hit this again to generate a couple of requests. And now we can finally switch to the Xray console. I'm going to need to reload here. Hopefully it shows this map now. And once this is done, there we go. We see an overview of all the services we have running. So this is what's called the service map. So, and I'm going to make that bigger. It doesn't work. Okay. So we see that web app is running. We have a name service running. We have a greeting service. We see a couple clients here, and these are here because we have also health checks running from the Kubernetes cluster. So it checks if the containers are up and running. That's why we see more clients coming into this. And the important one is of course this one, because this is where the load balancer is hidden behind. What we also see is that we have a couple errors in here. So we see something is read here, something is read in name, and something is read in greeting, and we're going to investigate that. The edges between here, and if you click on any of these things, you see that this is a request going from source to web app, from web app to greeting, and you can see the response distribution. So greeting is responding really quickly, and if I want to dive in here, I can mark this, and then if you have a broader distribution, you can also zoom in. And we can also see the response status. So we see most of the requests are okay. A couple of ones are returning an error, and a couple of ones are faulty. So we can now dive into that. So let's go to web app as the main service. Let's take a look at that. We see web app. It's hosted inside a container. This is coming from the ECS plugin now, and we can see, okay, there's a couple faulty requests that are passed on, and we've seen that when we hit the load balancer that we saw 503 errors. So we can take a look at that, and we see where these requests are coming from. And if I click here, I can filter. It updates the filter up here in this filter bar, and then down here we can see a list of traces, and you can scroll through them, you can sort them. So if we're going to take a look at a faulty one here, we'll see what has been recorded as the request went through our system. So we see that it hit web app. Up here we see the method, the response, duration, when the request was made. And then we see, okay, web app returned an error, greeting service was fine, and the name service, that one returned an error. And then down here you see that basically from the other direction, right? The upper one is the request seen from web app going out, and the lower ones are the traces as seen by greeting and name. They don't do any downstream calls, so no outgoing HTTP calls or calls to other AWS services, so we don't see much here. But we can click on this error, and then we see here, oh, we have an out of bounds exception. So now we immediately spotted one error which is in our application. So if we go to overview, we also see the so-called segment. This is the request that was made. We see that it's hosted in a container. We see the request information here, and under resources we should see more. There you see the pod name within our Kubernetes cluster. So we immediately know where this error is coming from. So if you have a lot of pods of name app running, then you immediately can see, okay, this one was where this error was generated. We also see in which AZ this was hosted and also on which EC2 instance. In case this is a very rare error, then you can also use that information to dive deeper. We also see Xray SDK information. The other ones are empty. We didn't track anyone except for the exception. So this is going to help us. So let's go in and try to fix this. So I need to switch to the name application, and this is the application. There's nothing I needed to add to do the tracing because everything was handled by the filter that was defined in web XML. And then I see this weird code, right? Somebody is generating a random number, and then sometimes it returns a name, and sometimes it just returns an error. And I'm just gonna comment this for demo purposes, and I'm gonna do this. Then I can switch to my console, and I can just rebuild this image. I can push it up, and while we wait for this, we can, because this is going to take a bit of time, it needs to compile. We can go back and take a look back at the service map. We can see everything here, and then let's go back in again, and let's take a look at a successful request. So we have, let's filter. So we have one here, and there we see additional information now. Now this was a successful one. So we see that web app called out to greeting and name. We see the requests. We can take a look at that one. We can see, okay, this was the request that was made. We can see it from the other services where the request came in and was also recorded in the tracing. And we can also see that we successfully made a call to our Lambda function. So our analytics part is also working properly. And we can even see that we wrote that record successfully to DynamoDB, and we can drill down even further and see how DynamoDB stored this in a table. So this is how a successful request looks like. So now you have seen the service map, and you have seen what kind of information the traces provide you. So let's quickly switch back and see, okay, we pushed our image. Now the way we deployed this is it's just a single container, and we will always pull the image from Docker Hub. So what I can do, I can just go ahead and delete this container. Then we have to wait a bit. It will delete the container, and then the deployment will notice this, bring up a new container, and then pull down the image so that we can see what kind of effect that has on our name app and the errors that were generated there. So we need to wait a bit. It always takes a bit of time. It needs to go delete the pod, bring up the new one, and then we should see something inside the Xray service map. So we can say, okay, let's take a look at this, what's happening. So we add watch, and we see, okay, the name one was created 44 seconds ago. It's still not ready. Web app is also returning errors. So web app is ready now. And now at some point, the name should also come back up. We can switch back to the console. We can refresh this here. Still updating. Yeah, and now a lot turned red because web app wasn't ready. Let's wait a bit. And then what we should see is that some of the errors within name will start to disappear. Because we fixed something, we're not throwing the 403 errors anymore, so we should see updates here. Let's check if the container is ready. Well, the container is ready, and then we should see the error rates changing here. So we should see more green in this circle and less yellow, but a couple of red ones will stay because we didn't fix the out of bounds error yet. So we have some more digging to do. And this should give you a pretty good overview of what Xray can do and how you can use that to trace requests going through the set of microservices. Now, this is just 3 services plus a Lambda function. Obviously, you will have many more services. And to make that easier for you to get started, we have prepared this GitHub repository. And it's still private, and you'll get the link in the slides, but what I'm going to do now is I'm just going to open source the repository for you. Hopefully that works now. Okay, I need to type the name. Good. And now you can go ahead and check out this repository and take a look at the instructions. You'll find the links to the applications here, and then you'll see how you can deploy these applications, how you can build the images, how we created the EKS cluster. Everything is in here, and then there you also see the service map that you should see when you deploy this code to your own account. So I hope this was a good overview of Xray, and I'm going to hand it back to Arun now.
All right. Thank you, Chris, so much. I always love the part where the way open source is live during the webinar. I particularly work in the open source team, so pushing a repo live and sharing with our customers is really exciting part of it. So let's move forward in the slides. I want to provide some additional information, and this is also relevant to some of the questions that have been asked, essentially. Now, one of the cool things at AWS, and if you have never played with AWS, you can always get started with the free tier of AWS. That gives you about 750 hours of compute time on a variety of instance types. So definitely get started with that. But particularly in context of Xray, I think you should be aware that the first 100,000 traces recorded are free. So if you're building a smaller application, then, and if you're getting a few traces here and there, then it should really be very easy for you. Now, these are trace records. If somebody else is recording the traces for you, if somebody else's account is in there, but then the first million traces retrieved or scanned are free. So there is a bit of a free tier which easily allows you to get started with it. And even beyond the free tier, the traces are really not that expensive. They're really recorded at $5 million per million trace. And the kind of capabilities that we showed today, how your end-to-end trace, all the way from your application, from greeting, from web app to greeting to name to API gateway to Lambda to Kubernetes, this could be all one trace. This is really high potential that is available to you. So definitely encourage you to take a look at it. I want to start summarizing here now. So what are the key takeaways here? The key points that we are trying to highlight over here is that, first of all, serverless and containers are the building blocks of modern applications. They truly encourage how microservices-based applications can be built. They truly make you think in those languages. They have those primitives that are available for you. You can use AWS Lambda for your serverless architecture very easily. You can use Amazon EKS for your container architecture as well. And another point that Chris highlighted in the demo also was that how Xray not only works with EKS, but it also works with ECS, which is Amazon's own container management solution. So you can choose ECS or EKS, and they're both building blocks for containers as such for you. the key part that you want to think about is always take a user-centric approach to monitor modern application. Don't think in terms of, simple logging or system log prints and all, because as your applications are a lot more distributed across multiple hosts, across multiple containers, across different languages, you want to adapt a technology that helps you scale and shows a customer impact. So really leverage Xray to not just debug, but quantify the customer impact and see how this will be really relevant to you. These are some of the useful links. This is where exactly Chris open sourced the GitHub repo. So feel free to use it, share it with your friends, share it with your customers, share it within your company. We also have a blog. Chris wrote a wonderful blog on application tracing on Kubernetes with AWS Xray. So highly recommend taking a look at that. And of course, there are websites for EKS and Xray. Now is actually the time for Q&A, but before we get started, I'm going to hand it over to Scott for some logistics.